Right, afternoon everyone. So we have 41. All right, 41 not inclusive me. So today we're going to be talking about elasticity. All right, the last subtopic of chapter 1. So let's get started. Okay, what is elasticity? Okay, based on your textbook, okay, elasticity is a property of the matter that enables an object to return to its original size and shape when the force that was acting on it is being removed. So, elasticity, you have to be aware that elasticity is actually not a physical quantity, okay, because physical quantity means that it can be measured, it's measurable, and it has value. So elasticity in SPM level is just a property, okay, of the matter that enables the object to return to its original size and shape when the force acting on it has been removed. So this statement, when the force acting on it has been removed, this one could be the force that is compressing, and also it can be the force that is actually extending. Okay, so the main reason why there is elasticity in materials is actually due to the force that is acting between the molecules inside the solid materials. So let's just say we have two molecules here right now. When we have these two molecules between each other, they actually have the attractive force, and at the same timing they will have a repulsive force. All right, so at normal situation, all right, at normal situation, both of the forces are actually balanced because the distance of separation between the atoms are actually fixed. The if you recall back your chemistry, the lattice structure of the molecules, they are actually in a structure whereby they are in a comfortable distance between the two molecules, all right, or the two atoms. So why are they at a comfortable or equilibrium position? Is because due to this attractive force and repulsive force, they are balanced in a way. All right, so solid has a fixed shape and a hard surface. So these are actually a few examples of elasticity. We have our mattress, we have the catapult. Obviously the catapult that we're talking about is actually the elastic band. We have the trampoline part, okay, and then for archery it is actually the string, right? And also the bow. Actually, more for archery, right? The more exact elasticity is actually the bow, right? The string, because usually the string that they use is actually not very elastic, but it's the bow that when they stretch it, the bow will actually bend. So when the bow bends and when you release the arrow, the bow will actually get back to its original shape. So it's actually the bow that is elastic. And then shock absorber is actually this one, the one that is normally at the tires, or if you were to go to children playground, all right, it would be usually at the seesaw area, right? The big huge springs over there. Okay, so these are a few examples and situation of involving elasticity. So this one I think I've sent it already. Okay, please, as usual, if you want the notes or you haven't printed out, you can just screenshot directly from the screen. Okay, so now this is actually not in your syllabus, but I think it's very important to explain this out to all of you. All right, when a wire is stretched by an external force, okay, this is the equilibrium positions of between the atoms. So when they stretch it with a force, okay, they will actually have stronger attractive force because when you stretch, they are already away from the equilibrium position. So the attractive force will actually become stronger. You see, attractive force grows more compared to the repulsive force. So when the force is being released, the attractive force is the one that will restore the original shape when the force applied to the wire is being removed. So when you stretch an item, the attractive force between the atom is the one that is trying to pull it back together. So when the force is being released, the let's just say the spring will actually go back to its original shape because of this attractive force. But if we were to compress a string, all right, we compress a spring, okay, and when you compress it, which means they're very close towards each other, when it gets closer towards each other, the repulsive force is the one that will become stronger. So when the compressing force is being released, All right, the repulsive force will actually push the atoms to restore back to the original shape when the force applied is being removed. So one thing that you all have to understand is that the force that is being removed can be a compression force or it can be an extension force. All right, so it depends on the situation. It's not always that it's being the force that it's being applied is actually the pulling away the extension force only. It can be compressed. Okay, so either way, this is actually the main reason behind the elasticity of the object. Okay, so I hope here, okay, as usual, if you have any question, just send a message inside the chat box. All right, so I'm gonna go next. Okay, so is an introduction of Hooke's law because we can't have an experiment right now. So as usual, virtually simulation is my best option. Okay, now, so if you look over here, this is a spring. Horizontal spring with a condition, one thing that I assume is there is no frictional force on the surface with the spring. Okay, so I assume there's no frictional force over here. So this is the equilibrium position. When I compress it, all right, when I compress this particular spring, and then when I let it go, it will actually get back to its original position. Okay, so okay, now I understand. This one is not the one that allows me to vibrate up and down. Okay, so when this is compressed, all these molecules will actually be pushed together. All right, so closer compared to its normal position. So when the force of compression is being removed, that is actually how the spring can get back to its original position. But when you pull it, extend it, okay, as long as one thing, as long as the elastic limit is not exceeded, okay, when we actually extend the force, all right, the spring, okay, it will actually cause the uh, position of the molecules to go further away from each other. So when the force is being released, it is the attractive force that is actually pulling the string back, the atoms back to go back to its original position. All right, so let's see this one. Okay, all right. So this is a simple thing that I want to show you guys. Let's see anything else here. Okay, so let's just say one thing. If I were to pull the force by 5 Newton, okay, it actually extends by 0.25. Let's see whether I can, okay. So I'm just going to do a very simple table at the side here. So I'm going to put this as my force. Unit that I'm going to use is Newton. And then this is the extension. The unit here that they use is actually meter. So if I were to extend the force by 5 Newton, the extension is 0.025 meter. If I extend it to 10 Newton, it would go to 0.050 meter. I continue to extend it to 15. And you would notice one thing, that when I extend the applied force by 5 Newton each time, it actually increases by 0.025. So I kind of predict that if, let's just say like this, it's going to be 0.125 for the extension. So one good thing about simulation is that it's going to be an ideal case situation. So it's definitely 0.125. So in a way that we can say that from this experiment, as the extension increases, as the applied force increases, the extension actually increase. And you would do notice that I did not measure from here. the spring position, but I measured from this equilibrium position. Equilibrium position is actually what we know as the normal length. Okay, so in experiment when we had the chance, either by next week or after your May test, we were going to carry out this experiment again, because paper 3 there's still a possibility for this experiment to come out. This is actually known as the original length. All right, you can actually look at your textbook also. This is our original length, which we label as L naught. And then here is actually our extension X. Okay, so the total from the end of the spring to the position whereby the spring is actually being extended, this is the total length, which is L naught plus extension. All right, so this is actually a simple experiment that we carry out online for Hooke's law. Okay, so I hope this one okay. So in your textbook, all right, what is the definition of Hooke's law? According to the textbook, Hooke's law states that number one, extension of a spring is directly proportionate to the force applied on the spring, provided means the condition that the elastic limit of the spring is not exceeded. So this is the keywords that you have to remember if the question asks you for what is Hooke's law means. All right, it's the extension of the spring directly proportionate. Now, when it says directly proportionate, means that if it's a graph, it will be a positive gradient straight line graph that passes through the origin. Okay, provided that the elastic limit is not exceeded, which means that in a short while we will explain what is elastic limit means. All right, from this statement of definition, okay, the relationship can actually be written as x, which is extension, directly proportionate to the force. So if you want to write an equal sign equation, that would be F equals to kx, whereby F is the applied force, K is actually the spring constant, and X is actually the extension of the spring. So F equals to Kx is the formula for Hooke's law. And please do take note, this spring constant has a lot of meanings that we will discuss today. Okay, so I hope this definition of Hooke's law you guys can catch up so far. Now, this is the experiment that we have in the textbook that we will carry out in the school lab when we get back to school. So over here, all right, we usually when we carry out this experiment, we will actually have the spring, and then we have the retort stand. Normally, I don't use two clamps. I put the spring just beside the ruler straight away. Okay, so I only use one clamp at the school experiment time. All right, so over here, if you would notice, all right, the pin is located, and our eye level is supposed to be at the pin position. Okay, so the extension of the spring is the increase in length of the spring when the stretch force is applied. Okay, what does it mean? It means that when there is nothing hanging onto the spring, that is known as the original length L naught. Okay, this is the original length. When we put load, or in other words, to say in exam, we're gonna in experiment, we're gonna put slotted mass. All right, we're going to put a slotted mass over there. So when we put the slotted mass, the spring will actually get extended. So the extended length we will actually measure as L. All right, the length, the new length is actually L. So the extension is actually here. All right, so in order to calculate extension, it is taking the length minus L naught. So in one thing is, in this particular picture that is in the textbook experiment, they put the zero at this level. Actually, you don't have to. You just have to hang it over there. Wherever position is that length, we can consider that as L naught already. Because when it get extended, what we want is actually the extension. So when it get extended, you just have to take this new length minus L naught, and this will be our extension value. All right, so we don't always have to put the zero of the meter ruler at the end of the spring. All right, we can just let it be sideways like this. Okay, so I hope that should be all right. Are you guys all right? Am I going too fast?
I'm good, sir.
Ian, you were saying something?
repeat the what LLO something,
Okay.
the one you were drawing over there. Yeah.
Here, this one.
No, no, no. The
This
mod.
one.
Yeah, that one.
All right.
Thank you, Joe.
All right. Okay, so as I said just now, over here we see that there's actually two clamps. One is actually to put the spring, the other one is to clamp the meter ruler. I usually don't really go and use two clamps because the amount of limited clamps in school. So I usually put the spring beside, hanging it beside the meter ruler like this. So why? Because over here you would notice that they draw this dotted line indicating that the spring is supposed to be placed at the 0 centimeter reading of the meter ruler. Now, due to the limit number of the limited quantity of the clamps, I hang it at the side here. So my original length, I will actually measure it over here. So let's just say if this reading is, for example, let's just say this reading is actually 15.5 centimeter. All right, from here down to here, that's 15.5 centimeter. So I'll take this reading as my original length. L naught equals to 15.5 centimeter, because that's not what we are going to plot. We're going to plot extension. So when I hang a slotted mass, the spring will actually get extended to, let's just say, at this position. And let's just say this position right now is 22.0 centimeter, for example. So when a slotted mass is measured, I'm going to put a slotted mass here. When we measure, we don't include the slotted mass. We only measure the position of the spring. So when the spring is being extended by the slotted mass, the reading actually goes until 22.0 centimeters. So that is my length, 22.0 centimeter. So in order to calculate extension using this formula, my extension x is equals to length minus L naught. So that would be 22.0 minus 15.5 centimeter. Where's my calculator? That would be 6.5 centimeters. So that is my extension. All right. So the most important thing, because when we plot a graph of Hooke's law, it's actually force against extension. All right. So the extension is the one that is important. It doesn't matter if we doesn't really start from the zero of the meter ruler. All right, Ian, you okay?
Yeah, Joe. Thanks.
All right. Okay, welcome. So now we go into elastic limit. Please do take note on this elastic limit. Okay, in the textbook they actually put a very small section on elastic limit over here, saying that ensure the extension of the spring does not exceed half of the original length, so that the spring is not overstretched and able to return to its original length. So what does this mean? Okay, the spring that we have in school is roughly around the length of this highlighter. Okay, so it's roughly around, let's just say, 10 centimeters. So when you stretch the, when you hang the slotted mass onto the spring, make sure it doesn't exceed half of the original length, which means what? 10, so it cannot exceed 15 centimeter. If you exceed 15, you might overstretch the spring. Okay, so normally you have to observe. Okay, you try to observe. How we observe is that we slowly put the spring and then we take out the slotted mass. Every single time we put a slotted mass inside there and we try to take it out back again. So let's see, I'm trying to show you guys the, give me one quick, where is my spring? Okay, no idea where's my spring already. The experiment. Okay, never mind. I'll show that to you guys back when I'm back in school. So we try not to exceed. And I just noticed one thing. Last year actually I did with your seniors, whereby instead of using the spring, all right, I actually gave them elastic bands. All right, when I gave them the elastic band, you know those rubber bands that is very, very long one, the white color type. I actually gave them use that experiment, you know. And when we carry out the experiment, right, I we all noticed that it wasn't a straight line. Because according to Hooke's law, the extension against force, it's supposed to be a straight line, you know. But when we use a elastic band, rubber band, it doesn't comes out with a straight line. It's a slightly curved line. Okay, it still increases. It still starts with the original position, right, from the origin, but the line is not a straight line. This is actually due to the property of rubber band and also springs. So this year, our experiment, we're going to go back to using a spring. Okay, so here, what does elastic limit means? Elastic limit means that it's a maximum force that can be applied to a spring such that the spring will be able to restore to its original length when the force is being removed. So if a force stretches a spring beyond its elastic limit, the spring cannot return back to its original length, even though the force no longer acts on it. This is like you if you will recall the experiment that we did regarding the tension of the string. When you exert too much force onto the string will actually break. All right. So when it actually breaks, it's no longer the same length already. So for elastic material, right, for elastic material like springs, like rubber bands, if you were to keep stretching it beyond its limit, and when you let go, the spring can no longer go back to its original position already. All right. So again, this one for elastic limit, I will have to show you to you in class because it's very difficult to show you over online. All the simulations are all ideal cases whereby there is no elastic limit for the online simulations. Okay, so over here, Hooke's law does not obey anymore. So if you look into these two graphs, do take note that these two graphs is two different graphs. This first graph is force over extension, and the lim at this part, this portion part, this one obeys Hooke's law. Right? It obeys Hooke's law, whereby when the force is being removed, it will actually go back to its original length. Okay, but at this position, this is the maximum force. Exceeding this maximum force, the spring or the material will not be able to go back to its original length already. It will actually be deformed already. That's what we usually say. All right. So, and then here is the graph of extension against force. This two graph is actually the thing is that the axis is the balik. All right. So don't think that, oh, you must draw a graph of force over extension. You can draw a graph of extension against force. All right. The only difference is that the curve is different only. Okay. So, and to identify the maximum force also still the same, just from the elastic limit. How do we identify the elastic limit? It is the position whereby the graph start to curve. All right, that is actually the elastic limit. Initially, it's a straight diagonal line. Then it start to curve already. Then this position is actually known as the elastic limit, and the corresponding force is actually the maximum force that the spring or the material can actually withstand. All right, while going back to the original shape and size. Okay, so this is actually for elastic limit. I hope okay before I proceed. All right, no response. Good to go. All right, next is actually force constant. Okay, Hooke's law, the formula is actually F equals to kx. All right, F is actually the applied force. Obviously, applied force means that it can be extension, it can be compression. X is actually the extension of the spring or the compression of the spring. All right, it can be the extension or compression of the spring. While K, this K is actually known as force constant or spring constant. All right, K is actually the force constant or spring constant. So what does this force constant or spring constant means? Okay, so number one definition, spring constant is the force required to produce 1 unit of extension on the spring. Obviously, this one is actually obtained by rearranging the formula of F equals to Kx, K is equals to F over X. So the definition for force constant or spring constant is the force required to produce a unit length of extension. Okay, so the unit for this, okay, unit for force is actually Newton. Let me change the color. Unit for force is actually Newton. Unit for extension, we use SI unit meter. Therefore, the unit for K is actually Newton per meter. Okay, so it depends on whether we are using meter, centimeter, or millimeter. Either way still can be acceptable. Okay, so what does this mean? It means that spring with larger force. Okay, let's go to analyzing this. K equals to F over X. If the spring constant is a big value, it actually means that higher force applied. All right. Higher spring constant value means you have a higher applied force, and also the spring extension is small, because only that way you can actually get a high spring constant value. Okay, so if you look at this sentence here also, a larger force constant is harder to extend. Why? You see here from this particular formula, when the spring constant is high, the force that is being applied is actually a very high force, but it will only extend a very small extension. Okay, meaning means where is my simulation? There. Okay, so if you see this particular spring constant right now, I'll show it to all of you. At a spring constant of 200 Newton per meter, if I apply the force of 35 Newton, or let's just say go to 50, it's easier for me to remember. 50 Newton, the extension is actually 0.25 meter. But if I were to increase it to 400 Newton, the extension actually drops. The same amount of force, the spring constant becomes higher, the extension becomes lower. All because of the formula of here, K equals to F over X. So remember one thing in physics, the formula is not only meant for you to do calculation, it is also meant for you to understand conceptually. All right. So if a larger spring constant needs a higher force, but it extends very small, so this is also what we considered as the spring to be more stiff. More stiff meaning means it's difficult for it to extend. All right. More stiff or higher stiffness means it is more difficult for us to extend or to compress the spring. All right. That all goes back to higher spring constant. So if let's just say if the spring constant is lower, all right, spring constant lower means that F over X, it means what? It means that the force, in order to produce a lower level of spring constant, the force is lower, all right, smaller value of force, and the extension is going to be very high. Extension is longer. So if the extension is longer means what? Means that if you just exert a little bit of, let's just say, a small amount of force, you pull it a little bit only, you just exert a small amount of force, the spring actually extends a lot. So when the spring extends a lot, this is actually what we call less stiff. All right, it's actually less stiff, but please do take note, we cannot consider it as less elastic or more elastic. Elasticity is already at the front few slides already. So what we can say is that the spring constant, if the spring constant is small, it just needs a little bit of force, but the extension is actually high, and it's actually much less stiff. So what does it mean is that if you look over here, I reduce the spring constant to 100, let's just say 100 Newton, same amount of force. The extension, the spring actually extended by 0.5 meter. All right. So this is actually lower spring constant, and we consider it as less stiff. All right. So please do take note now, we don't mention about elasticity anymore after this. All right. The only part that we mentioned about elasticity was the first few slides to say that it's a property of the object to return to its original shape and size when the force is being removed. Okay. Spring constant part, when we talk about Hooke's law formula, we will not talk about the elasticity anymore. Okay. So please do take note. I'm going to go to the next slide already. So I'm giving you guys 5 seconds to screenshot these slides. 1, 2, 3, 4, 5. Okay. Now let's go to can we write more flexible if the spring is less stiff? No. Xiang, it's better not to use the word more flexible. um I would prefer you guys to actually use back the terms that I have mentioned just now, which is spring constant, the force applied, the extension, and stiffness. All right, don't use the word flexible. I know last year I've been teaching you guys, if the answer is logical, they accept it. But over the past few weeks, when the examiners are actually marking the papers, they said that it is much more better to have the physical quantity and then mention the measurement. So being more flexible, it doesn't shows any the physical quantity, and it's something that we can't really measure. So that's actually not what we want in physics. So it's better for us to use back the terms of spring constant, the force applied, the extension, when we want to talk about stiffness. Okay, Shia? All right. Okay, so now let's go to analysis of the graph. Okay, so this analysis of a graph, I think I prefer to write it out by myself. Okay, so analysis of a graph is we're going to talk about the graph of force against extension. All right, so we have the force graph, and then we have the extension. So if it obeys Hooke's law, it's going to be a straight line graph. So what happens over here is that, let's talk about the gradient first. The first part is actually talking about the gradient. All right, please do learn how to analyze this. So we're going to analyze it two ways. One mathematics, the other one in physics. So we're going to analyze it in terms of mathematics first. So for gradient, all right, what we usually do is taking y2 minus y1 over x2 minus x1. Okay, so in terms of the gradient, that would be changes of f-axis over the changes of x-axis. So this is actually in terms of mathematics. But in terms of physics, how are we going to analyze? In terms of physics is whereby the y-axis is actually the force and the x-axis is actually our extension. So when we take Hooke's law formula, F equals to kx, and when I rearrange this equation to let F over x, it is actually the spring constant k. So the gradient for a force against extension graph is actually the spring constant. Spring constant or the force constant, as long as you know that that is actually K. All right, so this is actually the gradient for force against extension graph. Now, please be very careful in case the graph go and terbalik. All right, in case the graph terbalik. So I'm going to erase this off and show you guys. In case the graph is terbalik, what will it be? In case it's a graph of extension against force, still a straight line, okay? But here, the gradient, we still get y2 over y2 minus y1 over x2 minus x1, but it's actually the changes of x-axis over the changes of f-axis. Sorry, f-axis, blah. The changes of the force. Okay, so what happens here is that instead of it being spring constant, it will become 1 over k equals to changes of x over changes of f. So please be very careful. So if you want to find spring constant k, you have to inverse the gradient. It will be 1 over the gradient m if it's a graph of x against f. Alright, so please be very careful. This two graph is actually applicable to be coming out, alright, in the exams, in the experiments, but then it depends on what graph it is. So be very careful with this. Always refer to Hooke's law equation in order to find your gradient. Okay, so better screenshot that before I change slides. Okay, so that's why in the textbook, be very careful when we're talking about graph. What axis is it in the graph? So, where's my... Okay, so here is actually force against extension. So therefore, the gradient is actually the spring constant. So as what I mentioned just now, if the graph is actually extension against the force, then the gradient to find the spring constant is actually half of a grade, 1 over the gradient. So be very careful of what the graph asks you to draw or what graph is actually given to you. Now next is actually area under the graph. The next thing that we want to find. Okay, before that, for your information, right now we have one formula so far for elasticity. That's Hooke's law, F equals to kx. And we can find the gradient, which is actually a spring constant, all right, from the gradient of the graph. So next is actually area under the graph. Again, I'm going to show the whiteboard for a while. Again, a graph of force against extension. So a straight line because it obeys Hooke's law. So just now we found the gradient. So right now we want to find the area under the graph. So area under the graph is actually area of the polygon. So here we know that the area of the polygon is actually area of a triangle. So area of triangle, which is actually 1 over 2 of the base, which is actually x, multiplied by the height, which is actually f. So area under the graph is half of fx. And knowing that Hooke's law is f equals to kx, therefore 1 over 2 kx squared. So this is actually in terms of mathematics. So in terms of physics, what physical quantity is it? All right. The physical quantity for area under the graph is normally we take the y-axis, we multiply by the x-axis. So y-axis is the force, multiply x-axis, which is actually distance, the extension. Extension is actually the distance that is being extended. So force multiplied by extension, this is actually the work done. Work done to extend the spring. All right. And also because of one more thing, because work and energy can always be interchanged. Therefore, area under the graph is also the elastic potential energy. All right. So work done of the spring is also equivalent to the elastic potential energy. If you recall last year, we did mention that um, the SI unit for work is actually joules. The SI unit for energy is also joules. In order for you to do work, you need to have energy. All right, so they are always interlinked. They can be interchangeable. All right, so work is actually a change of energy. Therefore, area under the graph, which is actually half of kx squared or half of fx. These two formulas are actually two formulas. All right. It is actually to substitute a Hooke's law equation inside there. It can represent the work done to extend or compress the spring, and it is also the elastic potential energy of the spring. All right. So this is two informations that we can actually get from the gradient and also area under the graph for a force against extension graph. Okay, so for this graph, right, for area under the graph, it doesn't matter if it is force against extension or extension against force. Even if it's x against f, it's still going to give us the elastic potential energy. There's no change. You don't have to change anything like the gradient just now. All right, because here it is actually multiplication. Y-axis multiplied by x-axis. Okay, so I hope you guys can clarify regarding this. Okay, so far? So this is actually what is being mentioned in the textbook. Elastic potential energy is the work done to stretch the spring, so the average force multiplied by the extension of the spring, so that's half of Fx. Based on the graph, area under the graph is actually half of Fx. Therefore, the elastic potential energy is the area under the graph. So there is, to find energy, please do take note. To find energy, there is two formulas, either half of fx or half of kx squared. All right, so it's up to you which formula you want to memorize, and know this formula, this particular formula is not given out in the list of equation. All right, so this is for the graph. Up to here, any question? No question? Oh, okay.
Yep, okay, Chair.
All right, good. Okay, if no question, please kindly enter class point. Either you scan or you can actually use your laptop to enter. I'm typing out the URL at the chat box over there. So I only have 2% in here because I'm going to give you guys some exercises, seeing that I've talked for so long already. All right, I'm sending the class point QR code into the Telegram group under Forces and Motion 2 already. So I'm gonna show you guys the question. All right, for those who wants to get it, go and scan the code at the Telegram group. All right, so I'm gonna ask you guys to do a very simple one based on what we have already explained just now. Graph shows below actually shows this. So okay, so the graph below shows the relationship between the force and the extension of the spring. Calculate the spring constant based on the graph above. So find the answer for this. So I'm giving you guys around 3 minutes for you guys to try to calculate this question. Even though your May test is actually objective question, but always do objective question as though that is a structure question. So that is actually much more better. This question is actually image upload. So you can do your working at your paper or your book, and then after that use your phone to take the photo and upload into the ClassPoint app just now. Those of you who's actually using laptop, I think you can actually do the working at PowerPoint and then screenshot it before uploading it into the browser. Username Yong should be Hua-Yong, right? Hua-Yong, physics answer cannot to be in fraction. Physics answer, unless it's radioactive, the rest of the answer must be in decimal place. So don't use fraction in exam. I can tell you so far, I haven't seen an answer that I like. I baru cakap then I see. Alright, I'm giving an extension for another 30 seconds. Then I'm gonna close it already. Okay, I see another answer that I like, that really answer according to the question. 8 seconds before I close. 2, 1, 0. Okay. Alright. So from the working over here, okay, from all this working that I can see, I'm just going to randomly pick a few and insert them into the slides. Okay, I'm not going to pick Hua Yong's one because I already mentioned that the answer cannot be in fraction, so definitely cannot. Are you? How come terbalik one are you? Alright, I think that should be enough already. Okay, 1 quick minute. Mana itu pergi? Okay. Now, let me mark through the working. For your information, this question, alright, the question says that graph below shows the relationship. Where is it? The graph below shows the relationship between the force and the extension of the spring. Calculate the spring constant based on the graph above. One have to emphasize the word based on the graph above. So based on the graph above, you want to find the spring constant, means that spring constant is the gradient. So you're supposed to write gradient equals to the spring constant. Because it said based on the graph above, ma. Okay, so the spring constant K equals to, then you find your position. So let's just say you take 20 and 80, draw your dotted line. Obviously use a straight line, use a ruler, and then your point is actually 0, 0, and also 8, 20. Okay, so use the formula of y2 minus y1 over x2 minus x1, which is 20 minus 0 over 8 minus 0 equals to 20 divided by 8, 2.5. Now look at the unit. Unit for y-axis is Newton. Unit for x-axis is cm. So it's actually cm negative 1. This is the answer. This is the proper working because the question said based on the graph above. Okay? So you cannot take point 20 and 8 and then directly substitute into your working. So let's see. All right. Here, okay, directly substitute. Can we convert centimeter to meter? Can, no problem. All right, you can convert from centimeter to meter, no problem, which means if you convert from centimeter to meter, that would be, let's see, 8 centimeter to meter. Then the answer would be 250 Newton per meter, if I'm not wrong lah. Okay? 8 divided by 100, 20 divided by answer. Yeah, 250. So the answer is actually 250 Newton per meter. Okay? So here, actually, this working is wrong because the question says based on the graph. All right? If you're lucky and the examiner is not really concerned about it, they will still give you correct. But then if it's me, which I'm marking your exam paper, this is 1 mark. I won't give you mark for the substitution. So substitution kosong. All right, because you're supposed to use based on the graph. Okay. Next, here also, Xu Yang actually changed it to meter here already. So here I can accept the answer, but again, this part. All right, you're supposed to be finding it from the gradient. Then over here, also the same thing. Here can be accepted, but this part, try to use the proper method, the correct method to do it. We cannot always assume one thing. All right, from the past record that I know of lah, okay, I don't mark exam paper as you all know. Sometimes they are actually quite lenient, but we cannot always depend and praying for luck to happen. So we might as well follow what the question asks us to do, which is actually to find based on the graph. So spring constant based on the graph is actually the gradient. So you have to use the gradient formula to find the graph. Okay, so be very careful with that. Okay, Xinyan one also the same thing. All right, direct substitution. All right, without finding the gradient. So this one actually working wise is wrong, but answer is actually correct. You still get 1 mark. All right, the rest of you also, if as long as your answer is correct, you still get 1 mark. Substitution, I'm going to mark based on SPM style. If your substitution or your working is wrong, but your answer is correct, you still get a mark for the answer. Okay? Now, this is the one that I like. Thank you, Qishuan, for writing this one. So he actually really used the gradient formula and really did this. So Qishuan actually get 2 out of 2. Okay? Then here also Shavin. Alright, but one thing, Shavin, this working, I don't really like the working so much because of one thing. What are you calculating? Alright, substitution wise, yes, I can give you 1 mark. But then one thing, even the unit also you didn't bother writing it. When you don't write the unit, 0. Alright, and please, Shavin, identify what you're finding. You're finding for the spring constant, so write K over there. Okay, now, so we found that the spring constant K answer is actually 2.5 Newton centimeter negative 1. Or some of you converted to meter, that would be 250 Newton per meter. My question is, what does the value of the spring constant means? So can you please write your answer? What do you think that value means? What does the value of the spring constant calculated in the previous question means? 'Right, I'll be waiting until the 3 minutes time. For information, this question that I'm giving to you guys, these are the questions that came out before in SPM. Huh? 20 seconds to go before I close the submission. Alright. So let's see the answers. Okay. Question was, what does the value of the spring constant calculated from the previous question means? So let's see some of your answers. How stiff the spring is, the tendency of the spring to extend, amount of force needed to extend the spring, Sabrina, the force required to produce 1 unit of extension of the spring. Zixian actually says 2.5 Newton of force is needed to extend the spring by 1 centimeter. Out of this whole entire page, Zixian's the only one who got it correct. Okay, so now let's see. Here, no one got it correct from this slide. Eject, the spring needs 2.5 Newton to extend 1 centimeter, correct? So a measure of stiffness of the spring, which is 25 Newton per centimeter, Chongwei Sala is 2.5 Newton. It is how stiff the spring is. The spring will have 1 unit of extension. 1 unit of extension, the unit is what you need with 2.5 Newton. All right, it takes 2.5 Newton of force to make the spring extend by 1 centimeter. Good job, Daniel. All right, 2.5 needed Newton needed to produce 1 centimeter of extension. Xingming, should I even screenshot that and send that to Mr. Teo? The amount of force needed for the spring to extend 1 centimeter. How much amount of force, Adelia? The maximum amount of force that can be exerted for the spring to stretch until it's unable to return. Sorry. All right. It shows how stiff the spring is. No. Force needed to extend. No. Okay. Now let's continue. Sham said it's a measure of the stiffness of the spring. Salah. So we only have 1, 2, 3. Here tak ada. 4. 4% out of so many. Okay. So what does the value means? The value is 2.5 Newton per centimeter. So if you take the formula, always remember, recall back taking the formula. All right, the formula for spring constant is force over extension. So if it's 2.5 Newton per centimeter, means it's 2.5 Newton over 1 centimeter. So that's the reason why a 2.5 a spring constant of 2.5 Newton per centimeter means that a force of 2.5 Newton is needed to extend the spring to 1 centimeter. So this is actually what it meant of spring constant value. All right. So please do take note. All right. Came out for SPM before. Okay. So I'm going to go next. All right. So try to answer this question. I'm giving 5 minutes to answer this question. And take this 5 minutes as a break also. We'll come back in another 5 minutes time. So while waiting for the break to end, please do the question. Right, I'm back and I already see there are some answers around coming in. So I'm going to close submission at 6-minute marker. Would have advised next time if you guys is going to screenshot, take photo of your answers, right? Try not to open the flash. That's why sometimes when you take the photo, the center is bright, the side is dark. No worries, Rob. Alright, so I've already exceeded my 6 minutes. Where is my marker? Okay, so I have closed the submissions. Okay, so I'm going to insert, insert, insert. Randomly going to pick and insert. Out of these three, okay, good. I know Sanjeev working, I have to tilt it a bit. Um, okay, now let's see. Questions here. Question asks, a spring of the original length is actually 10 centimeter is stretched, okay, by a load of 0.4 kg to a length of 12 centimeter. So calculate the spring constant first thing. So you have L naught 10 cm, you have the mass, which is 0.4 kg. It has been extended to a length of 12 centimeter. So to calculate the spring constant and calculate the length of the spring, if a load of mass 0.4 kg is replaced by a load of mass 0.6 kg. So I'm going to show you my working first. So first thing first, to find the spring constant, which is K equals to F over X. So number one, the extension X is L minus L naught. So that will be 12 minus 10 equals to 2 cm. And then the force is actually the weight, which is equals to mg. So that would be 0.4 times 9.81. Okay, 0.4 times 9.81. So that would be 3.924 Newton. So therefore, K equals to F over X, 3.924 over 2. So the spring constant is 1.962 Newton centimeter negative 1. You don't have to change to meter. I repeat, don't have to change to meter. So now the question B actually says calculate the length of the spring if a load of 0.4 kg is replaced by a load of 0.6 kg. So all you have to do is actually use back the spring constant, okay, and use the formula of F equals to Kx. So X equals to the force over the spring constant. The force is actually 0.6 kg now. Multiply it with 9.81 to change it to the weight. Over spring constant is 1.962. 0.6 times 9.81 divided by 1.962. The extension right now is 3 centimeter, but the question asks for the length of the spring. So the length of the new spring is L0 plus extension. That would be 10 plus 3. Answer is 13 centimeter. All right, so that is the actual working. If those of you who do not know how to do, please screenshot in 5, 4, 3, 2, 1. I'm going to start marking. Okay, so here Ejet's working. All right, Ejet, please do one thing. Right, this is F equals to like this. Okay, then you get here. You see how did you get the 2? Please do the working step by step as though the examiner knows nothing. Even though, yes, this is a full mark question answer because the substitution and the final answer and unit is there, but try to do the working more clearly. And to me, I will put a big question mark here. Why? Because I have no idea what you are doing here. I have no idea what you're doing here. At the very least, over here, you wrote k equals to f over x. I know you're finding for the spring constant. But at b, I have no idea what you're doing. So I'm just going to put a question mark, even though I can see the working very obvious. Okay? So here, Aliza's working 0.4 times 9.81. Okay, this one I can accept because I can see the substitution over here. So I'm going to accept this answer. And then here, also correct. All right, this one is wrong. It's not supposed to be 12. It's supposed to be 10. All right, so here only get 1 mark out of 2 probably. All right, Aliza. Working wise, for me it's very good working. Okay, now let's look at Rabika. Rabika's working okay, step by step. Okay, you change to meter. All right, good. Can be acceptable. Change to meter already, and then here 5.89. Okay. Rob, actually you don't have to complicate yourself by doing this. You can just directly write f equals to kx, k equals to, sorry, you can directly use the formula straight. Because you already found the k here. Alright. But I know you like the ratio, working wise is still correct, but for me you have wasted a little bit of time, and if you're careless, you might have some careless mistake over here also. Alright, so please be very, very careful, Arabica. Will I still accept? Yes, I will still accept. But as I said, there might be careless mistakes, so you have to be careful with that. Alright, Hua Yong's working, let's see, 0.4 Newton, Hua Yong. Sudah salah. Alright, this one is already wrong. Okay, now everyone please learn. This is error carry forward. Hua Yong actually found this one. He forgotten to change the mass to weight. So when he calculated, he actually got the wrong answer. But when he substitute into here, this is still acceptable. Okay, but Hua Yong again, apa you tengah buat over here? Same thing like Ejet, even though I can see what you're trying to do, but working wise is not really proper. Okay, Hua Yong? Alright, Avdash working, let's see. Okay, good. Again, apa you tengah buat kat sini? If I see this in paper 2 in mid-year and trial, I'm going to give 0. The rest of you also. Hua Yong also. Ejet also. Alright, Avdash also. Part A, you all did the working and the steps properly. Part B, how come cannot do properly leh? Alright, next we have Ayu's working. Let's see. 4 Newton. Ayu, upper cell 4 Newton. Remember our G is supposed to be 9.81 meter per second square. So this one is definitely wrong already because you substituted the value of G wrongly. But then because here you substitute wrongly, this one I penalize you, but here I will give you 1 mark for substitution. Okay? But here salah. So here also will be salah. Okay. Error carry forward, only the substitution part you will get marks, but the answer unit part you will get it wrong. Okay. Last, I think Sanjay one is the last before I want to proceed already. Okay. Alright. K again, Sanjay salah. Here wrong, but substitute over here correct. The force is supposed to be the weight. The weight is supposed to be mg. So it's supposed to be 0.4 times 9.81, not times 10. Please, please remember. All right, remember G is supposed to be 9.81. So Sanjeev, you're working also same like IU. I only can give you the substitution, but the rest of it will be wrong. SPM memang macam tu ah. Alright, so very quickly, just last one. Okay, this is correct. Load. Again, ratio method. Okay, ratio method can be acceptable, but please be very careful. Zixian, you didn't fill up the full thing. The question is asking for the length. So it's actually 10 plus 3, 13 centimeter. Alright, so you didn't answer the last part. Okay? Alright, okay. Please be very careful. Exam cannot tell the examiner you forgot. Okay, I'm going to skip this part and I'm going to go to the last second part of elasticity. Alright, we're going to talk about factors that affect elasticity. This kind of factors is more on how to say modification questions, choices questions, decision making questions. So please be very aware, because normally these are the questions that has more marks. Factors that affect elasticity. All right, spring constant over here. When we talk about the factors that affects the elasticity of the material, we describe it in terms of the spring constant. Okay, so we don't talk about elasticity, we only talk about the factors that affect it in terms of spring constants, about the stiffness. All right, so over here, okay, so what we can say is actually the spring constant. All right, recall back when we talk about the spring constant K. Okay, if the spring constant is high, if the spring constant is high, it actually means that the force applied is high, the extension of spring is low, meaning means that we can consider it as more stiff. All right, the materials is actually more stiff. If you say that the spring constant is low spring constant, so means that force applied is low, the extension of spring is high, and hence it is less stiff. All right, so this is actually what we're going to be talking about. When we talk about the factors, we're going to talk about the spring constant, the force, the extension, and whether it is stiff or not stiff. Okay, and please do take note, actually, one thing, there is a formula for stiffness. All right, there's a formula and value for stiffness. It's just that we do not introduce to students right now in SPM level. All right, even for elasticity also, there is actually a formula for elasticity, but we don't introduce that to students yet. Okay, so just be satisfied with the force Hooke's laws equation and also understanding this particular thing that I just mentioned out. Okay, so we're going to start with the first factor. All right, this is actually based on your textbook. According to the textbook, the value of the spring constant, what happened? Okay, value of the spring constant is actually affected by, all right, it's affected by the materials of the spring, the length of the spring, the diameter of the spring, and the thickness of the spring. So these are four things. All right. If they mention that the spring constant is the same, which means that it is made out of the same material, the length of the spring is the same, the diameter of the spring is the same, the thickness of the spring is also the same. So we're going to talk more about these four factors, and do take note, there are four factors. So which means in modification part, these are the four factors that you can include of. All right. So material of the spring, different materials, all right, it will change according to the type of materials, which we will discuss. That is already in the textbook actually. The spring, the length of the spring, whether the spring is longer or shorter. Shorter spring, shorter spring will have higher spring constant, right? Shorter spring will have higher spring constant. Higher spring constant means what? Go back to the previous slide. Higher spring constant means the force applied needs to be high in order for it to extend a little bit. So higher spring constant means it's more stiff. So shorter length of the spring means it is more stiff. All right, it's more difficult to extend. Longer spring means that lower spring constant. Lower spring constant means that you just need a little bit of force. It will extend very long, means that it's less stiff. Okay? Then diameter of the spring. Now, the difference between diameter of the spring and thickness of the wire is diameter of the spring means overall the spring is big or is it small. Okay? So diameter of the spring, if the diameter is small, the spring constant is high. If the diameter of the spring is bigger, the spring constant is actually lower, means it's less stiff. All right, and thickness of the spring wire, one small little wire, if the diameter is small, all right, please do take note. Smaller diameter means smaller area. All right, means smaller area of the wire. It can also mean smaller radius. They selalu go in and confuse student with this. All right, smaller diameter of the wire, because we know wires are actually circled. All right, the cross-sectional area is actually circled. So smaller diameter means smaller radius. It also can mean smaller area. So please take note on that. So smaller diameter, the spring constant is lower. Lower spring constant means what? Less force, higher extension, less stiff. Okay? So that is how we try to analyze using the formula for spring constant. Okay, so now let's start. The first one. Okay, so the first one is actually elasticity. This is what the textbook gives us. This is what I add on some more. Okay. Now, so over here, all right, the length of the spring, the shorter the spring, the stiffer the spring, and the bigger the spring constant value. So if I were to write a summary, all right, so the shorter the spring, shorter length of spring, all right, it means that it is a higher spring constant. It has a higher spring constant. Again, spring constant formula is force over extension, meaning means more force to extend the spring. And then the extension of spring is small, meaning mean it is stiffer. All right, it's more stiff. So this is actually how we analyze whether it is higher spring constant or not. So, and in other words, in terms of modification, decision making, and also uh, inventing new stuff, this is actually the option, all right? This is the option, the choice, and all this down here is actually the reason. You use a shorter spring. Why? So that it can be a higher spring constant. Why? Because more force is needed to extend the spring. Why? The extension is small. And why? Because it's much more stiffer. All right, depends on what the question wants. Okay, if in terms of graph, all right, in terms of graph, how do we see? All right, first thing first, look at the graph, extension against force. So how do I know which is actually stiffer or not? So I will actually usually what I do is, okay, let's see apa saya nak buat sekarang. Okay, So what I do is I will draw a horizontal straight line, okay? And then I will draw the extension downwards. Okay? So this is how I analyze in when I'm doing the questions now, okay? So over here, what is written at the same extension, let's just say this is spring A and this is spring B. Okay? Spring A, same extension, needed a force of FA, and spring B actually needs a force of FB. So this means that when you extend the same force, the spring extend the same amount, let's just say 10 centimeter. Okay, spring A actually needs less force compared to spring B. So what does it mean? It means that spring B is stiffer. Why stiffer? Because needs higher force to extend. All right, it needs higher force to extend. Need higher force to extend means the spring constant K is higher. And true enough, spring B is a shorter spring. Okay, but for spring A, how do I talk about spring A? Spring A is less stiff. Why is it less stiff? Because require needs less force to extend the spring. And then the spring constant, because the force is actually less already. So when the force is less, the spring constant is lower. And in terms of length, lower spring constant means longer spring. Okay, so I hope I'm teaching you guys how to conceptually answer spring questions already right now. Okay, so better screenshot that before I go to the next slides. 5, 4, 3, 2, 1. Next, diameter. Diameter of the spring here depends on whether it's a big diameter. Okay, do take note one thing. When we talk about all these factors, let's just say right now we are dealing with diameter. When we change the diameter, we assume the rest is constant. All right, when we actually talk about the diameter of the spring, which means we manipulate the spring constant, the diameter of the spring, the rest is the constant, and then the spring constant will become the responding variable. So always remember, when we want to talk about something, the rest must be constant. We can only manipulate and change one thing at a time. We cannot change too many things at the same timing, or else we will never identify the cause and the effect. Okay, so right now when we're talking about the diameter, here the diameter is that, where is my, okay, smaller diameter is actually stiffer. All right, smaller diameter means it's stiffer. Bigger diameter means it's actually softer. The opposite word for stiffness is actually soft. So here, what does it mean? I prefer to type. Okay, this actually means that when diameter of the spring is small, diameter of the spring is small means what? It means that the area of the spring is small, the radius of the spring is small. Right, so this is actually what it meant. So when the diameter of the spring is small, the spring constant is actually higher. All right, when the spring constant is higher, from the formula of force over extension, Ian, I'll answer that in a short while. When the spring constant is higher, force over the extension means the higher force is needed. to extend the spring, and then the extension is small. So if the extension is small, we identify that the spring is actually a stiff spring. Okay, so same thing if we were to talk about when the diameter of spring is big. Diameter of the spring is big, means lower spring constant. Lower spring constant means in order to get lower spring constant, we need lower force needed to extend the spring, but the extension would be high. All right, and this is what we call it as a soft spring or a less stiff spring. All right, so this is actually what we meant. All right, Ian's question, can we say that shorter spring has lower elastic limit? No, Ian, we cannot talk about the elastic limit in terms of the spring constant. Because the elastic limit base has a lot of other things that they need to require. We can only do experiment to identify out the elastic limit. Okay, so shorter spring or longer spring does not represent the elastic limit of it. Okay, so this is actually for diameter. I'm going to go to the next slide. Better screenshot that in 5, 4, 3, 2, 1. Now, thickness of the wire. Thickness of the wire is actually depending on this. All right. If you can see the left and the left is darker. Darker actually indicates thicker wire. Please do put a statement over there. Darker wire indicates thicker wire. All right, because in the exam, the only way that they can identify whether is it a thick or a thin wire is through the thickness. All right. If it's dark, all right, it's actually a thick. If it's actually very fine, that's actually very thin material. So over here, the diameter, if we're going to talk about the diameter, the thickness of the wire. So thickness of the wire is low. For example, lower thickness. It actually means that the spring constant is lower. And the spring constant is lower means that the force needed is lower, is less to extend. But then the extension is long. All right, and this is whereby we call it as a soft wire or a less stiff wire or spring. Sorry. All right. Hence, the thickness of the if the thickness of the wire is thicker, okay, the spring constant is higher, more force needed to extend, but the extension is low. All right, when the extension is low, we consider it as a stiff spring. Okay, so I hope this one you guys are okay. All right, so far everyone okay?
Yeah, sure.
Very good.
Sir.
Thank you for responding, the two of you. Okay, last is actually the type of the materials. Now, type of materials, this one, by hook or by crook, you have to memorize lah. Okay, we have steel, copper, and aluminium. Normally, we would prefer copper. Okay, now copper is actually a soft material. Steel is actually much more stiffer. And obviously, aluminium is the most stiff material. So over here, what does it mean? It means that in terms of increasing property, okay, in terms of increasing property. So let's talk about spring constant. Okay, increasing spring constant meaning means okay. Suddenly okay. In aluminium is actually has a lower spring constant compared to copper, and then steel has a higher spring constant. What does it mean? It means that force required to extend aluminium needs more force compared to copper, but the one that needs the most force to extend is actually steel. Okay, and now when we talk about the extension of the spring, uh, aluminium. Let's see. I need to make sure that I don't do things wrongly. Increasing. Okay. Steel has the least extension, followed by copper, and then aluminium is the last. Aluminium has the longest extension. Steel has the shortest extension. So in terms of stiffness refers back to the extension. So steel is actually more stiffness. Copper would be stiffer. Okay. Stiffness will have to go back to spring constant. So it would be aluminium, then followed by copper, and finally steel. So which means steel is the most stiff compared to copper and aluminium. It is more easy to extend aluminium, so aluminium is actually the softest. All right, so this is actually in terms of material. This one you got no choice, you have to memorize this. Okay? Because material that they normally choose is actually aluminium, copper, or steel. All right, it depends on what kind of materials that we want to use. Remember, sometimes in modification question, they ask choose the material used to make the spring. All right, so the materials you can actually talk about these three different things. All right, you either choose, normally we would either choose aluminium or steel or copper. All right, so depends on how you want to explain. And obviously, copper is much more preferable because copper is much more cheaper. Okay, that's why normally in lab actually we use copper and steel to compare. We seldom use aluminium to compare. Okay, all right. So far up to here, I think should be okay. We're gonna talk about the last one right now. So before I go to the last one, the rest all alright, yeah. I'm going to go to the last part of elasticity. So I'm gonna finish in terms of concept. Then next week when we go to class, we're gonna do exercises for elasticity. All right. So right now, when we want to talk about the concept wise, it's actually spring. Okay. So I'm gonna take a very simple data here. If I take one spring, I apply a force of 50 Newton. This is one. When I apply a force of 50 Newton, the extension, let's see what's the extension value will be. 50 Newton, the extension is 0.25 meter. Now, normally for springs, we will have arrangement of the spring. So in terms of arrangement of the spring, let's just say this is actually side by side, which we know it as a series. All right, a series, not series, a parallel arrangement. All right, a parallel arrangement. If I apply a 50 Newton force, let's see what is the extension. The value is actually 0.125. 0.125 here, it actually means that taking these two extension and divided it by 2, you will actually get 0.125 meter. All right. So for parallel extension, when you have the same load, they are being shared by two different springs. All right. I repeat, parallel springs, when you have the same load, it actually the extension the load is actually being shared equally by the two springs, provided the spring constant and everything is the same, the length is the same, the material diameter, wide, thickness, all is the same. Okay, so if let's just say we arrange it in terms of series, this is series, side by side, I extend the force to 50 Newton again, but look right now, the extension is 0.5 meter. All right, 0.5 meter means times 2 of this. So what does it mean? So in series, actually, all right, in series, when you have the same amount of force extending, pulling the two springs together, both of the spring individually will extend the same amount. Like for example, just now it extended 0.025 meter. So when the same amount of force, which is 50 Newton being pulled, both spring actually extended 0.025 meter. So the total extension is 0.050 meter. That's why the extension of the spring is 2x. Now, how do you remember this? For me, um, identifying the arrangement of series means the elder sibling. Okay, I am gonna erase all this first. Okay, for me, how do I recall? This is actually the elder sibling, and this is the younger sibling. So general cases are not every single house also like that. So if let's just say the parents actually scold one child, both of them actually at the same situation, they argued or one or whatever it is. When the parents scold one child, the other child will actually experience the same amount of scolding. So they for here, if the force is actually the same, then they will actually extend the same amount. When the parents scold them, they will scold both child the same, both gonna the same equal amount of scolding. All right. So that is how I remember for spring. So the extension is actually doubled. Total extension is doubled because one spring extend X, another spring extend another one. So up and down like this, this is how I identify it as siblings. All right. And then the in another words to say, when the load, all right, load is W, it will extend the same amount of K. The force constant would be K, all right, one spring. But if you have two springs, it will extend two times, but the load is the same. So the spring constant is actually divided into two. Divided into two means the spring constant actually drop. When the spring constant drop, which means extension is more, obviously the extension is more because it's become 2x already, right? So it is actually softer or less stiff when the spring is actually placed in series. You would notice one thing. In total, the spring actually increase in length. So when it increased in length, the spring constant actually reduced. Okay? So this is identical springs in series. Next is actually identical springs parallel. Parallel for me, it is like a mother and a father. All right. When looking after the same child, which is the force, they share the burden. Okay. I repeat, in parallel is representing by a mother and a father. When they look after the same child, they share the load. So the extension is actually divided by 2 when there's two springs, identical springs in parallel. So the total extension of the spring is x over 2 only. Okay? So let's just say one thing. When the springs are actually placed in parallel with the same amount of load, all right, the extension decrease already ma. When the extension decrease according to F over X, same amount of load means F is constant. The spring constant K is inversely proportionate to the extension. So when the extension has reduced, the spring constant will increase. That's why when identical spring placed in parallel, the spring constant actually doubled. Alright, the spring constant actually doubled up. So double up means stiffer arrangement. Okay, that's the reason why when you go out and you play, you see the kids seesaw nowadays, they don't put one spring in the middle. They actually, if they play seesaw nowadays, the recent one is I brought my kids to IKEA, Ikano the power center there. They, instead of using one spring, they actually put two strings parallel to each other. Main reason is to make it stiffer. Why? Because when it's stiffer, you need more force in order for it to compress. So it can withstand more weight of the kids. Obviously, they will write a maximum weight means how much over there lah. Okay? So this is actually arrangement of identical springs in parallel. So this question, I will further explain it in terms of calculation in class. Now let's talk about factors on a weak spring system and a stronger system. I have only 2 more slides to go. Okay, so if it is a longer spring, it's actually a weak system. Now, weak system means longer spring, bigger diameter, meaning means what? The spring constant is lower. Spring constant lower means force required is less, extension is high, and it's actually less stiff. So, how do you have less stiff? Less stiff means the spring is long, the diameter of the coil is big, it's made out of copper, it is made out of thin wire, and it's arranged in series. Higher extension. Okay? So, even though longer spring means flexible, you need to replace it very frequently. It breaks very easily. It exceed the spring easily extend and it will exceed the elastic limit very easily. High maintenance. All right. So these are all the weak spring system that we have to avoid. All right. So remember, this is to avoid. If you want it to be more flexible, okay, lor, long spring, lor. Okay. But what is a good spring system? A good spring system means the spring constant is high. Good spring constant is high means the force required is actually higher. The extension would be less and it's actually stiffer. How to make a stiffer spring system? You use shorter spring. Use a smaller diameter of the coil. It is made out of steel. It is made out of thick wire and is arranged in parallel so that the force is actually shared equally. Why a strong system is not so flexible? When it's not so flexible, you don't have to replace it so often. It will not break easily either, and it's lower maintenance. Why lower maintenance? Because it doesn't break easily, ma. And the spring does not easily extend. So these are the factors that you need to remember because this is the question that actually requires more marks in paper 2. Okay? So up to here, any question?
Rachel, what does it mean by maintenance of a spring?
Maintenance means that how often you need to change the spring, how often you need to uh You need to put oil to the spring so that it doesn't have too much of friction, those kind of maintenance.
Oh, okay. That's true.
All right. Anything else? Anyone else? All okay, huh? Okay, so if all okay conceptual wise of elasticity, I'm done already. All right. Next week when we go back to school, we will discuss more of the question first. Maybe the experiment I will do that after our May test. Okay. So if there is nothing else, then I shall stop the class here today.